A1, B, C. Okay. So what are the statistical properties, or what are the properties of the OLS estimator? That's our question. So what are the properties of the OLS estimator if we know this model, X is full rank, we have strict exogeneity, and our errors are neither autocorrelated nor heteroscedastic. Yes. Yes. Someone else, what does blue mean? Yeah. So it's efficient, best, linear, unbiased estimator. So it's efficient. So that's good. What happens when we have A2 instead of A1, so that we don't have strict exogeneity anymore, but weak exogeneity? Yeah. It's biased, but asymptotically unbiased. Unbiased, so it's still consistent. It's still consistent. So in large samples, we can still use it as wrong. So we only have a real issue in small problems. Yeah.
Is consistent basically the same as
No, for consistency we need one more thing. So consistency has two in the way it's defined here. It has two conditions. So one is asymptotically unbiased, and what else has to happen for a consistent estimator? Yeah. Yes, so for consistency we do have one asymptotic unbiasedness. So consistency in the sense of mean squared consistency. We have two things. We have one asymptotic unbiasedness. Biasness, and true that the variance of the estimator goes to 0. Right? So, and this is exactly correct. What that then entails, or what that tells us, is that if n goes to infinity, the probability that the estimator goes to the true value is 1. Right? So it's very high. It converges to 1. So the more information we have, so the more data we have, the closer our estimator to the true value. And that's our minimum, or that's a very important condition for an estimator, because if we want to be able to interpret the the estimated parameters. Okay, so yeah, so we don't have an unbiased estimator. That also means that it's not blue anymore, but because blue is an assumption or is a property that belongs to unbiased estimator, right? So it's not the best linear asymptotically unbiased estimator. So that's why the blue really wants this summary. That's very basically neat. Okay, so then next, what happens when B and C are violated? So that means we have auto correlated, or let's say and or, because we don't have both at the same time always. But the result is the same. And or that's errors. So what happens to our OS estimator then? Yeah.
I think the variance of our OS estimator increases, and therefore leads to problems regarding like hypothesis tests.
Yes. Exactly. So we and what that means in these terms is what is very interesting is that we still have an unbiased estimator. Biased estimator with OLS. So if we would only want to interpret the value of the estimator, then we would actually be fine. The issue arises with all of our inference because, first of all, it's no longer efficient. So we don't have the best linear unbiased estimator anymore. We can find one that is better. And also the variance of beta hat OLS is no longer sigma squared x prime x inverse, but no. I have to check, I think I know. But it is x prime x inverse x prime omega x, x prime x inverse. And this omega here would be the variance covariance matrix of the error, which we call U or E. I think on this exercise sheet it's called E. Let me check. No. You are there and you right? So the issue is, and the issue with that is that if you use your usual packages or functions that we always do on the computer, that the computer doesn't know that we have this issue, and it's going to like standardly just calculate sigma squared x prime x inverse. Right? So this is no longer the correct, this would then no longer be the correct estimate for this variance. So if you remember, if we assume, so this was our estimated variance of the OLS estimator given x was sigma squared hat, and And that means that the tests that we usually do or that are printed in our summary are not valid. So it's not that they're too large or that they're too little or something like this. No, they're wrong, right? So this, because it's calculated with a function that is not a consistent estimator for our variance. We would need another estimator for that, and that's more tricky. This estimator is more tricky because it's harder for us to get an estimator for a sigma squared. It's easier for us to get an estimate for one value, sigma squared, than for this whole matrix omega, which has n by n entries, right? So that's kind of the issue that arises then. That estimating sigma squared is very easy. It's one value. We do have a lot of information in the best case, but estimating omega is very hard because we have omega is an n by n matrix and has, I don't want to lie, but yeah, the whole diagonal and all of the lower diagonal elements, like this many different entries. Yeah. So that's kind of a problem. So it's not an equation, so we might find a better estimate. And we have this estimator issue. And that's also, if we know this is also going to lead us to the two ways we solve this problem. And there's one solution. One is that we estimate the GLS estimator, or use the GLS estimator. Which is efficient and unbiased and also consistent, but that's an addition. Yeah, that's one solution. Or the second solution is that we still use OLS because it's unbiased. It's unbiased, but with consistent standard errors. Or, yeah, let's call them robust because in a lot of cases we say that they are robust to this problem with robust standard errors. And there are two different kinds. We have the white standard errors or New Way West. The white. There are also a lot of notes there, but the white standard errors, which is because this economist or econometrician White is the first one to develop this. The white standard errors that are robust to heteroscedasticity. And then we have the New Way West or hex standard errors that take it one step further, so they're a little bit younger errors that are robust to both. So HAC stands for heteroscedastic. Heteroscedastic auto correlation consistent error. And it's true because and I have no idea how they call it. Let me if they're consistent estimators for consistent sorry guys, my spelling today is bad. Estimators for this x prime x inverse x prime omega x x prime x inverse. Any questions? Because this is where we are. Just as a reminder, I expect you all to know this when the exam comes, because that's kind of what I'm going to ask, what we're going to ask in the exam. Yeah.
And also regarding the exam, you need to understand like in detail what those half and y senators are doing, like what the measures and parameters.
Yeah, so I mean, I would say what's important to note is that the hack and right standard errors, they find a way to incorporate, to estimate these elements, all of these elements, so that the x variables are weighted correctly, kind of, yeah? So this is what's going on. I know that the formulas look crazy, and yeah, I mean, and I also wouldn't be able, I mean, we're not even looking at how to prove that and how to calculate them or something. We show that they are the consistent estimator. But what's important to note is that they estimate these omega values, and the difference between them is that they assume that we have they still assume that we have a diagonal matrix, so they only estimate the n different, or try to get the n different variances on the main diagonal, and the near west they get the whole matrix, right? Where they kind of try with all of this stuff to get the whole matrix. So because the issue in most cases is what is this omega? What is this thing? Right? So yeah, but more than that, I mean. Okay. So with this, I think we're good, well prepared to look at our little example that we on the exercise. Well, I ran everything already. Okay, so let's look at the exercise here. So what we have is this data set Phillips, because it's kind of Phillips because of the Phillips curve. If you're in macro, then you hopefully know what the Phillips curve is. It's a very simple representation of this, and a very, very simple example. Okay, so we only have the inflation and the change in unemployment here. And we have data for quarterly inflation and the change in unemployment, which is called DU. So change in unemployment, DU, D stands for change. For the delta, so change in unemployment, so I hope that doesn't confuse you. So we have, and for the period of 1987 to 2009. And what we're interested in is this relationship, and we want to estimate this parameter beta 2. So we're interested in the parameter, we want to know the size of the parameter, and we want to be able to make tests about the parameter, right? So the first step that we do is look at the simple model, plot and estimate it with small s as usual. Then the next step, we plot the residuals to see if we see any issues there regarding heteroscedasticity or autocorrelation. And then we look at the autocorrelation function, which is just a function that gives you information about how the error is, or a variable is correlated with itself. So it's always the correlation between like the value with the value before and or 2 steps before and so on. And then we see something about this covariance matrix E. Then in B we're supposed to test what we saw in the, because we don't want to rely on eyeballing. We don't want to just eyeball plots, but we want to check this with a statistical test. And then for that we're supposed to describe the test procedure and interpret the results. And what I can also already tell you is that it might come up that you have to describe test procedures in the exam. You usually don't have to know the test statistic because the formulas are too long, but this specific test statistic is actually very, very simple. So same as the T statistic, those I would guess you would know, right? So we're going to see. And as you see, we also did there, he tells that you employ a statistical test. There are many statistical tests. We are going to use one specifically, but we can also use a lot of other tests. And if we ask you in the exam to explain a test, then you can choose a test for the specific question. So if we use describe a test for autocorrelation, then you can describe one of the tests, right? So you don't have to describe like a specific. If we ask for a specific test, obviously you have to describe that one. But in this case, it's very open. So you could, if you do this at home, you could do something else. And I will do mine. Okay, and see, and then we get the result, interpret the result of this test, and then we're going to handle the result. So as this exercise is structured, I hope you already realized that we're going to find autocorrelation, and then we're going to solve this autocorrelation by estimating this with GLS, or one is feasible GLS, or the second option is use the hack standard errors that are heteroscedastic, autocorrelated, consistent standard errors, and what else, right? So what we talked about, what I talked about before this. Okay, so first, I think I need some packages because I didn't want to do too much myself. So we're going to see which packages is going to do what. Then first, I already loaded the data and I wanted to just plot our data very quickly, just so you see how the unemployment, the change in unemployment and inflation looks like during this period. So let's see, we have both of these variables in percent. So we have inflation as a change in price in percent, and we have the unemployment also as unemployment change also percent. And what you kind of see if you look, I mean, I would not show this graph in the beginning of a presentation if I would want to argue that you can clearly see that these two are completely related. So I think, but what you kind of see is that in the beginning, inflation goes up, unemployment change goes a little bit down, then inflation goes down, unemployment goes a little bit up. So you kind of see this what we expect from theory. Okay, so, but we also see lots of other stuff. Okay, so let's see. What we were supposed to do next is estimate the model by OS. So let's just have a look at this very quickly. And get the results. So the OLS estimate for this beta, which is the coefficient here, is minus 0.52. So, question for you. All of the variables are in percent. What is the interpretation of this estimate? Yeah.
I think it's in percentage points.
Yeah.
So if, in this case, unemployment rises by 1%, inflation considers by 1 percentage point, also 4%.
Yeah, it decreases by 0.52%. That's good. Yeah. So if the change in unemployment increases by 1 percentage point, inflation goes down by 0.52%. We do have a negative relationship here, what we kind of saw in the plot, and we also have like inference here, but as we discussed, we don't look at this inference before, or we don't want to look at this before we check the residuals. So usually if you do your own empirical study, you would estimate the model with some estimation method, and then you would check the residuals before you interpret the results too much. Right? So don't be happy about results that might then fall apart because you find for example, adverse elasticity in that case. Okay, so, and to look at the residuals, we first look at the plot of the residuals. So you see it here. And the line, the red dotted line is at 0 because the residuals should randomly move around 0. Right, so that's our main focus. So random residuals, let's say, look at this. So just so we are here, the plot should be should be just a random cloud of points with the same around 0. Also with this same variance, so in nice straight bands, right? So I'm trying like this. It should be nice, straight, kind of shown in this corridor that kind of gives you the variance. And so it should be this. Right. But how does this look like? Well, I feel like I always give too much away with the plots already before I give you the chance to say something. But I hope you guys see that in the first 18 observations, the residuals are all positive. Right? So that's a large positive correlation between the residuals, because from a positive residual, we get a positive residual, we get a positive residual, blah, 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 blah. It should move way more about 0. Then we get a time, like in the middle of the sample, we get a time of a lot of negative residuals, also a sign of a positive correlation between our residuals. And then only in this little last couple of here, maybe here in this time, here, there, these residuals look a little bit not like without achievement, because the rest is like this. It looks like they're correlated. So should be this, not for heteroscedasticity. Oopsie. So the residual plot for heteroscedasticity, for example, would look like this. So we have maybe sometimes a very small variance in the beginning of the sample or in the, or depending on whatever you have. And then on the end, we get a large variance, like this little funnel. That's a very common sign of heteroscedasticity, for example. Okay. And for autocorrelation, we see something that it's like above 0, below 0, above 0, below 0, like this. Okay, so this already looks like heteroscedasticity, so let's look at the autocorrelation function. Oops. I think we saw one in the lecture. Okay, so this is the autocorrelation function for our OLS residuals. And what that tells us that in the first line here is for the correlation between the observations with itself, so that's the variance, right? So that's horizon 0. Yeah, and then all of the other ones here are the correlation between horizon 1, horizon 2, 3, 4, 5, and so on. And what that means is that in our sample, there is, and the blue dotted lines here are confidence bands, kind of, and give you information about the test that it's the confidence band for the test that these parameters are 0, right? And if they're above 0, we can say, well, this order here for horizon 1, we do have autocorrelation in the residuals, and this in this case is up to horizon 6, and then even for 8 we get a significantly different estimate for the correlation. Yeah, so also in this case the autocorrelation function also looks like autocorrelation. What for a variable that is not autocorrelated, all of the first line, so the variance would be different from 0, so this is fine here, but all of the other lines would be below this blue dotted line, and or inside this blue dotted line, because they can also get negative, right? So if you have not autocorrelated residuals, you will see that all of these lines are below the blue dotted line, which is not the case here. So this is also kind of already a test. Yeah.
What is the
the horizon, right? So it's always in point t to t minus 1 or t minus 2. So this is like the horizon h. And so it's always the correlation between a specific point or to the point before that. Yeah? And because you have n or t observations, right, so you can always calculate the sample correlation between always one point at the next, and then one point at the next, and one point at the next.
So the whole, every value is connected to like one standing value. So the 15 is like 15 away from 1.
No, it's always like for each and every observation, because you have 10 observations, you always have like, you calculate it as the weighted sum, as the average of, you get the correlation between 1 and 15, 2 and 16, blah, blah. And then with that you will calculate the sample correlation between all of these. And I think it's easier to think about it for just horizon 1. So this is so we get the horizon, right? So it's 1, 2, 3, 4, 5 until whatever. But for horizon 1, it's pretty simple. So you calculate the correlation between always today and yesterday, and then for each and every observation that you make, because it's over time, right? So it's always like observation 1 to 2, then 2 to 3, 3 to 4. And all of those give you information about the correlation between a value and its previous value, right? So because for each value you do get a previous value, so you can calculate the covariance, sample covariance, and that's just as we always say. Usually it's like ui minus 1.
Do they all refer to one singular standing line? Or
No.
Okay, it's
So
just
it's always like you move along, you kind of move along the observation. So no, I don't want that. That's not the correct way to write it. Oops. Maybe this is easier. So you start at observation 1, 2, and then so on. And you get to observation t, and then that doesn't make sense. Plus 1, plus 2, plus 3, so on until observation n or observation large t or whatever, like all of your whole sample. Right? And then for the theoretical moment, you would assume that this goes on forever. And for the statistical, well, for the population moment, you would calculate the correlation between these two, and between these two, and between these two, these two, these two, sum them up, and take the average. Like, use these, right? And then for 2, you get 2. And so on. Yeah. calculate the product of the observation, the mean observations, for our errors. The meaning isn't so necessary because they are still centered around 0, so their mean is 0. So you multiply your the observation in one period with the previous period, and then divide that by the variance, your sample variance, and that is the correlation. And then you sum, if you sum all of the products up, so that you get the covariance, and then you divide it by the sample variance. And you can do this for each horizon, and that's what is shown in the autocorrelation function. So these are not like, it's not a continuous function where you would combine all of these dots, right? So okay, so now that we kind of saw that we do have an autocorrelation problem, we do have a problem. We are supposed to test this with a statistical test. And the test that I'm using is the Gefei-FIONA test. Because that's very simple and I think just a nice simple test. Test for autocorrelation, which is also a Lagrange multiplier test. So the Lagrange multiplier test is just the class of tests, and this is for autocorrelation. For heteroscedasticity, there's also a Lagrange multiplier test. It's called the Broich-Cayley test. And they work very similarly, but there's a distinction, and that's important to know how this works. Okay, so we first are supposed to kind of describe how this works, how this test works. So the test procedure. So the first part, you see in R it's just a line because there's a function for this. You could also do it by yourself. You could code it yourself. It's also very quick. So you might want to, and you can definitely do that yourself, and you are able to do this. So the first step that you do is estimate the model with OLS, which we've already done. The model with OLS and save the residuals, which we've also already done. Because it's an issue with the residuals, right? So we need the residuals somehow. And then in the second step, we are going to, or this works with an auxiliary regression. We are going to do it in a different regression. And in that, and there's the difference between the test for autocorrelation, the Lagrange multiplier test for autocorrelation, and for heteroscedasticity. For autocorrelation, we regress the residual on its past. Right? So just the residual on its past. And all of the regressors that we have in our original regression. So in this case, we change how it's going. So and then we regress it on its past, right? And we can, whatever we choose as the the number of legs of the residuals. That gives us how, what kind of order of autocorrelation you're testing. So this is a test on autocorrelation. Of order P, right? Because what we're testing is that all of these regressors, all of these correlations between residuals and its path are zero. So it's a joint hypothesis here against the alternative of no autocorrelation. And if we, after we do this auxiliary regression, we can calculate the test statistic, which is the Lagrange multiplier test statistic, which is just the number of observations, t, large T, times the R squared of the auxiliary regression. And this follows a chi-square distribution with P degrees of freedom. And that is what I mean when I said this test statistic is super easy because we just multiply the number of observations with the R squared from the auxiliary regression. And I mean, I know we're going to show you an example, but obviously that's not going to hold all of the different examples that we've ever done. But in the previous exam, we, for example, gave you the output for this auxiliary regression, and you would have to see from this auxiliary output from the auxiliary regression one, what test it is, what problem this test has, and then also calculate the test statistic and also make a test decision. So that was kind of one of the exercises, one of the tasks of the exam, right? So after seeing the auxiliary regression, you can deduce what's going on. Yeah. So and this plot just looks like the summary statistic just looks like the normal output, right? And you have all of the different information. So you see the formula, you see your coefficient, you see the variables that are included, you know the R squared. So by just looking at this, you are able to tell us what kind of model is estimated there and also everything else. Okay, so in R it's very quick because we have this nice function of the Gauge-Godfrey test. In this case, we just include the regression, inflation on the change in unemployment, and select an order. And I just tested for the order 1 correlation, test for zero correlation of order up to 1. You can also raise this, so you can also do 2 or 3 or whatever, and that's the choice that has to be made. I just chose one kind of randomly, and then you see the test result, the LM test statistic, which is 27. It's from a chi-square distribution, and just as a reminder, the chi-square distribution looks kind of like a T distribution, so it's like a sum-shaped thing that is only positive, right? So, and in this case, we have a chi-square distribution, we are feeding 1, and you also get the p-value, which is 0. here. Obviously, and probably most of you saw this, the null hypothesis, if we assume that all of these parameters are zero, the null hypothesis then is that it's no autocorrelation, and the alternative is that we have autocorrelation. And here, with the p-value of 0, we can reject the null hypothesis. So we conclude that we have an autocorrelation problem. Okay. Any questions?
I have a question. How do we see the zero of the p-value? Could you please? It is the
P-value is something to the power of,
upward line.
that's 10 to the power of minus 17. So we get here a 1.4 times 10 to the power of minus 7. 7, was it 7?
Yeah.
So this 7 means we get 7 zeros.
Okay, this is the reason, all right.
So it's not exactly 0. And it's also never going to show you exactly 0, right? So the computer doesn't stop. So what happens? So I don't know how far, but I think until 16. I think you get a 10 to the minus 16 in the end, something like this. And what happens is that as the computer calculates this p-value and then realizes, oh well, this is a lot of zeros, and then at some point, at some number of zeros, it just stops. And it obviously doesn't get the complete zero. So what you're always going to get is something 1.5 times 10 to the power of minus 16. But that's just a numerical issue for the computer. So because they cannot calculate that these values to be exactly zero. So So what we are going to do now is the two solutions that we have in C. We use the GLS estimate with GLS, and in D we calculate named or use heck and errors. So for GLS, there's also a function GLS, and the issue is that we need to make an assumption about the correlation between our errors. And if we would know more information and we would make this assumption, we could just include it here in the correlation. We don't assume to know anything at all. So we are estimating this. And if we estimate this correlation, then we get in the realm of feasible GLS, which you also saw on the slides somewhere. And we're not doing like the last part of the feasible GLS. Right? So this is, I think, the slide for feasible GLS. So what we do first is we calculate the OLS, done that, obtained the errors, residuals did that. Now we're going to use the residuals to estimate the parameter here of the omega. So we want the correlation because we have autocorrelation problems. So we estimate the correlation. In this case, it's gamma as the correlation coefficient. And then we use this estimated gamma omega dependent on gamma to compute our GLS estimator. We use that in the function, the GLS function. And then if you would want to go further, you could iterate this. So for feasible GLS, you usually, or you would want to do this all over again. So we get the residual of this feasible GLS, of this GLS estimation, then calculate again the relationship between the residuals, and then enter that again and over again to again, in the end, get a good estimate of the omega. So it is an iterative process. We're not going to do the iterative part. So the first thing we need to do is find the covariance matrix. So I'm using the autocorrelation, the auto regression function here to get the calculate the autoregressive coefficients of the residuals. For that, you just put the residuals, like the variable, into the AR function. Here, I'm not imposing an order. So what we can also do, because we did the order 1 here for the Borch-Gottfried test, we tested this for order 1, we could also just fix the order here to 1. Didn't do this. I let the function choose the order by the Econometric criterion, which is a selection criterion that for comparing models with each other. And then, so that's what's happening there. And then we include in the GLS function, you see we have again just our regression function. And then in addition to that, we now need to use the correlation, which is in this case the correlation matrix of these residuals with order that is chosen by. And then, so that's kind of on, and then in the end, we get so this is the output, the summary of the GLS estimator. So you see here the minus 0.807 is the GLS estimate here, and then we get standard error and also the usual t-values here. So if we compare this to the OLS estimator, they are a little bit different, but with the standard errors, I think if we would calculate the confidence bands, the OLS estimate would lie in this confidence band of our GLS estimator. But these are different, right? And what we can still do is test if this estimator is significantly different from 0. We can use these standard errors for a lot of other things. Get a lot of other tests. This standard test here is that is the question if it's statistically different from 0, and we could definitely interpret this here. And here you again see this. I mean, this comes up a lot. If the p-values are very small, this comes up a lot. This is here 1 times 10 to the power of minus 3. So that's a 0.0001. So it's a 0.1%, right? So this is a very small p-value. So we can reject the null hypothesis again that that the parameter is 0. Okay. The upside here, so the positive point, is that we get an efficient estimate. So we get an estimate with a very small variance. Efficient estimate. What's the downside? problem with the GLS is that we either need an additional assumption. So the large issue is, what is omega? What is omega? Is omega. So we either need an additional assumption and an estimate, or an estimate for omega, right? And the problem is, if that's wrong, the whole thing is invalid. Okay? So the whole procedure hinges on this additional assumption, and sometimes we do not want to make this additional assumption. And for that, we want to then use the hex-standard errors, which does not need additional assumption. No additional assumption. But obviously, the downside is that it's not efficient. So, and do this in R is very, very quick. We just have to specify that we want to use the hex-standard error. And for that, we do have a function which is very nice, which is v-cof tech, which variance for variance matrix tech. And we just need to give into this function our model that we estimated, our LS model, and then we can produce new coefficient tests for this specific case. So we can do the coefficient tests that are standard in the summary for this LS model, and the variance covariance matrix here is then our hex errors that we specified before. So it's kind of, yeah. So if we now look at the t-tests for this, we see that if we so you see that it's also very quick, right? So no additional assumption. And what's happening here then is we get the same estimate, right? Because we didn't estimate the parameters again. So these minus 0.527 is the same as before, as in the very beginning. Let's see. Yeah. So these estimates are exactly the same. The difference between them, with these two tables, are the standard errors and the t-values. And that's because the standard errors and the t-values in the original summary, which is in this case 0.229, is just not calculated with a correct formula. And this year is still based on the sigma squared x prime x inverse, which is just not correct anymore. So if we use hex-standard errors, these are going to change. So in this case, the hex-standard errors are actually, so the OLS standard errors are actually 0.3. Okay? And that then also shows the issue. If you don't control for this autocorrelation, you underestimate your standard errors. Right? So your inference might be actually wrong. So while in the first case here, we would get a p-value of -0.02, so we would reject this null hypothesis at alpha 5%. With the hex-standard errors, we get a 0.086, which is larger than 5, so we would actually not be able to reject the null hypothesis that the estimate is 0, that the parameter is 0 at the 5% significance level, but only at the 10% significance level. Right? So that's kind of the issue that we face. And if we have this kind of issue that under standard errors we lose significance because our standard errors are inflated, that might be a good reason to actually then go to the GLS or try to do something else, because in the GLS standard errors we get a standard error of 0.23, which is smaller than this estimated hex standard errors. Yeah, and there we can reject the null hypothesis again, so we get a significant estimator here. Okay. So these are kind of the pitfalls. But what is really, really nice about the hex standard errors is that you can implement them very quickly because you just have OLS, if you don't need any additional assumption. And actually some people also, I mean, there's also an argument to be made for larger standard errors than needed, right? Because if you do have like inflated standard error or estimate this with OS, and then get larger standard errors, but with these larger standard errors can still reject the null hypothesis or that you made, then your results are kind of even more credible, right? Because it even works with our larger standard errors. So this is kind of, yeah, so there are arguments for both sides, and in practice, you usually see, in a lot of cases, if autocorrelation or heteroscedasticity is really at the center of the issue, people just use the hex standard errors because it's if that's not your research focus, you don't want to think about that. You have a lot of other things going on, so people just throw them in there. So in a lot of empirical papers, you're going to see people using these robust heteroscedasticity